Click the bell icon to get latest videos from Ekeeda.
Hello friends, in today's session we are going to study about a technique which converts hard water into soft water. It not only converts hard water, it can convert any kind of hard water into soft water. Now when I'm talking about any kind of water, there are basically two kinds of hard waters, that is permanent hard water and temporary hard water. Any process which can convert permanent hard water into soft water can definitely convert temporary hard water into soft water. This process converts the permanent hardness of hard water into soft water. Let us see in this session the exact procedure and the method for the same. Hot and cold lime soda process or method. What is the principle of it? In this method, hard water is treated with calculated amount of slaked lime, that is nothing but CaOH twice, and soda ash Na2CO3 in reaction tanks, so as to convert hardness producing chemicals into insoluble compounds, which are then removed by settling and filtration. So here in this method, in today's session, we are going to study about the different chemical processes and different chemical reactions which are actually happening in those tanks, which convert the hardness of the water into the softness, that is, they convert the hard impure water into pure soft water. Lime required for softening is calculated by a formula as L is equals to 74 upon 100 times of what? That is temporary calcium plus twice into temporary magnesium plus permanent of calcium, magnesium, aluminium and ferrous plus CO2 plus HCO3 minus NaAlO2. What exactly is this formula? Whenever we want to convert hard water into soft water, we do not have the exact amount of lime or soda ash to be put into it, because it always depends on the quantity of water and always depends on the amount of impurities which are present in that quantity of water. You cannot add excess of it, otherwise it will start reacting with water and form other kind of impurities in it. We need to be very specific and exact about how much lime or how much soda ash do we have to add in to get this procedure into action, and that is the reason why we have this formula 74 by 100 into the temporary of the impurities and permanent of the impurities. Apart from temporary and permanent impurities, we have to keep in consideration carbon dioxide, because carbon dioxide is also one of the major reasons for hardness of water, and plus we have the different ions present in the water. In a similar manner, we also have to calculate the requirement of soda. Again, for soda we have 106 upon 100, but over here we have permanent Ca2 plus Mg2 plus Al3 plus Fe3 plus H plus ions plus AlCl3 minus HCO3 minus NaHCO3. This is the formula required for my soda content in it. Normally about 10% excess of chemicals are added in the reaction tanks to complete the reaction quickly. So now we have these formulas, but we are just allowed to add 10% excess of what is required. We cannot allow more than that. If we put a little excess of it, it will help in speeding up the reactions, and the reactions will happen faster, and because of that we'll get a pure water faster. But apart from that, more than 10% is not desirable. Let us see the reactions with lime. Lime reacts in the following ways during softening of water. The first thing that lime tries to do is to neutralize any free acid present. For example, I have HCl, H2SO4. HCl and H2SO4 are nothing but my acids plus CaOH twice, forming CaCl2 plus 2H2O. Let us see the balancing of this reaction. I have 2HCl plus CaOH twice on my reactant side. Let us count the number of H's on the reactant side. I have 2H, and over here also I have H2. That means I have in all 4 hydrogens on my reactant side. Moving on to the product side, I have H2 and twice. This is nothing but 4 hydrogens. That means the number of hydrogens on the reactant side and the product side are balanced. Apart from that, we have 2 Cl on my reactant side, forming Cl2 on the product side. That means the number of chlorines on my reactant side and the product side are also balanced, forming CaOH twice. Over here, let's take calcium. On my reactant side I have 1 calcium, On the entire product side also I have 1 calcium, and finally I have oxygen, that is 2 oxygens on my reactant side and 2 oxygens on my product side. Thus the reaction 2HCl plus CaOH twice forming CaCl2 plus twice H2O is a balanced reaction. Let us have a look with the reaction of H2SO4. We have H2SO4 plus CaOH twice forming CaSO4 plus twice H2O. So H2SO4, let us count the number of hydrogens on my reactant side. I have H2 and OH twice, that means 2 plus 2, 4 hydrogens on my reactant side. On my product side I have 2 into 2, 2H2, 2 into 2, 4 hydrogens on my product side. Moving on to sulfur S, I have over here in my entire reactant side I have 1, on my entire product side also I have 1. Oxygen O4 plus O2, O4 plus this is OH twice, and that's the reason why this will become O2. 4 plus 2, that is 6. Over here we have O4 plus 2 into O, that means O4 plus 2O, 4 plus 2, that is 6. Then we have calcium, 1 on the reactant side, 1 on the product side. Thus this is also my completely balanced reaction. H2SO4 plus CaOH twice forming CaSO4 plus twice H2O. The second is to precipitate iron and aluminium salts, if any, as hydroxide. The first thing that lime did was reaction with acids and try to remove acids from water. The second thing lime will do is it will precipitate iron and aluminium salt if at all they are present. So here I have Al2SO4 thrice. This is nothing but my aluminium salt plus 3 CaOH twice. Now what happens over here is it forms 2 AlOH thrice, which is a precipitate which can be easily filtered out, plus thrice CaSO4. Let us look at the balancing of this reaction. Over here I have aluminium 2, and we all know that the valency or the amount of electrons or the amount of atoms which are needed to satisfy that aluminium is thrice. The valency of aluminium is thrice, and that is the reason why we have taken 3 CaOH twice, because this OH has to go to aluminium, and this is Al2, that means 3 of one aluminium plus 3 of another aluminium. That means the overall valency will be 6 times, and that is the reason why we will need 6 OH to fulfill this valency, and that is the reason we have taken 3 CaOH twice. That means 3 into 2, that is 6, and that's the reason why this 6 OHs will go and stick with these 2 aluminiums in the form of 3 and 3 and will form AlOH thrice, which will be a precipitate. Now let us see the balancing of the reaction with each and every element. Starting off with aluminium, we have Al2, 2 aluminiums on my entire reactant side. On my product side also I have 2 aluminiums. Then moving on to S, over here I have S, which is thrice. Over here also in my CaSO4, which is thrice, so I have my S as thrice. Oxygen, over here I have 4 3s are 12, plus over here I have OH, that is twice, that means 2 into 3, that means 12 plus 2 into 3, 12 plus 6, that is 18. I'll explain this again. Over here I have 4 into 3, 12, plus 2 into 3, 6, that means 12 plus 6, that is 18 oxygens on my reactant side. On my product side, let us see, I have 3 into 2, 6. Over here I have 6. Why? Because OH is thrice, so 3 into 2, 3 into 2, 6 oxygens over here, plus 3 CaSO4. Over here I have O4, which is multiplied by 3, so 4 3s are 12, so 6 plus 12 is 18. That means I have 18 oxygens on my reactant side, 18 oxygens on my product side. Moving on to my calcium, I have 3 Ca over here, I have 3 Ca over here. And finally my hydrogen, in my entire reactant side I have 2 hydrogens into 3, that means 3 2s are 6. Over here I have 3 hydrogens into 2, that is 3 2s are 6. That means this is my entire balanced reaction. It is very important to balance out the entire reactions to fulfill each and every valency of each and every element. The second reaction is FeSO4 plus CaOH twice forming FeOH twice, which is again a precipitate, plus CaSO4. Now FeSO4 is on my reactant side. Let us actually see the balancing of each and every element. Instead of SO4 over here, OH is being attached. Since SO4 has two valencies but OH has just one valency, we need two OHs to replace the SO4 part which is attached to Fe. So over here FeSO4 will be replaced, the SO4 will be replaced by OH twice. Let us see the balancing of each and every element of it. On my reactant side I have one Fe, on my product side I have one Fe. And reactant side has one S, that is sulfur, product side also has one S. O4, the number of oxygens, O4 plus O2, O4 plus O2, 4 plus 2 is 6, 6 oxygens on my reactant side, O2 plus O4, 2 plus 4 is 6, 6 oxygens on my product side. Then I have Ca which is 1, Ca is 1 over here also, H is twice on my reactant side, H is twice on my product side as well. Thus this is my entire balanced reaction. Moving ahead, we have 2 FeOH twice plus H2O plus half O2. Half O2 is nothing but my nascent oxygen, but we generally write half O2 instead of nascent oxygen because nascent oxygen is unstable. So we have FeOH twice plus H2O plus half O2 forming FeOH thrice, which is a precipitate. So over here, let us see the balancing of it. Over here, we have 2 Fe's on my reactant side, 2 Fe's on my product side. Let us count the number of oxygens. Over here, we have O2 which is twice. In my FeOH twice, I have O2 which is twice, that means I have 4 oxygens plus 1 which is 5th oxygen plus half O2. Do not consider this as O2, consider this as half O2. Half O2 is what? O2 upon 2, that means 2 oxygens divided by 2, that means 1 oxygen. That means over here we have 2 into 2, 4 plus 1, 5 plus 1, 6. 6 oxygens on my reactant side, and this is nothing but O3 into 2, that is 3 2s are 6, 6 oxygens on my product side. Then we have H2 plus H. H2 into 2 plus H2. What is happening over here? We have H2 into 2. That means 2 into 2, 4 plus H2, that is 6. 4 plus 2, 6. 6 hydrogens on my reactant side forming 6 hydrogens on my product side. This is again a balanced reaction. The third kind of reactions by lime are to precipitate dissolved CO2 as CaCO3. So I have CO2 plus CaOH twice forming CaCO3 precipitate plus H2O. So what is happening over here is my Ca2 is reacting with CaOH twice and forming CaCO3. CaCO3 is again a precipitate, that means it is insoluble in water. It can be easily filtered out, plus we'll get pure form of water in it. Let us see the balancing of these kind of reactions. Over here I have 1 carbon, over here I have 1 carbon. Let's count the number of oxygens, O2 and O2. 2 plus 2 is 4 on my reactant side. Over here I have 3 plus 1 is 4 on my product side. Calcium is 1 on my reactant side, calcium is 1 on my product side, and finally the hydrogens are 2 and hydrogens are 2 on both the sides. The last kind of reaction is to precipitate calcium bicarbonate as CaCO3. So I have calcium bicarbonate, that is CaHCO3 twice, which is nothing but a soluble impurity, a bicarbonate, plus CaOH twice forming CaCO3, which is a precipitate, plus twice H2O. So what is happening over here is, let us count the number of calciums. Over here we do not have 1 calcium. Generally on all the reactions we used to have 1 calcium over here and 1 calcium over here, but we have calcium plus calcium. Why? Because we are actually precipitating calcium bicarbonate over here. So we have Ca plus Ca, that is 2 Cas on my reactant side and 2 Cas on my product side. Let us count the number of hydrogens we have. Over here we have H2 because this is twice. Over here also we have H2 because OH is also twice. So 2 plus 2, 4. Over here we have 2 H2. So over here also we have 4 hydrogens. Carbon, over here in my entire reactant side I have 1 carbon which is twice. So C is 2 over here, and over here also I have 2 C's. So carbon is also balanced. And finally we'll balance out the oxygens. This is 3 into 2. 3, that is twice. 3 into 2 is 6 plus oxygen twice over here. So 6 plus 2 is 8. And over here we have 3 into 2, 6 plus 2 over here, that is 8. So oxygens are also balanced. So this is again a balanced reaction. to precipitate magnesium salts as hydroxide. So over here what do we have? We have different kinds of magnesium salts, and these magnesium salts react with it to form insoluble salts. That means these magnesium salts are soluble in water, which are there on my reactant side, but what it forms on my product side are all insoluble, and because of that they can be easily filtered out. Let's look at each and every reaction over here. We have MgHCO3 twice plus 2CaOH twice forming 2CaCO3, which is a precipitate, plus MgOH twice plus twice H2O. So what is happening over here is my MgHCO3 twice is getting converted into MgOH twice. This HCO3 twice is a bicarbonate, but OH twice is just an hydroxide. It's much easier to remove a magnesium hydroxide from water than to remove a magnesium bicarbonate from it. Plus 2CaOH twice. Now this 2CaOH twice is the main reason why this MgHCO3 twice is getting converted into my magnesium hydroxide. It forms CaCO3, which is a precipitate. It can be easily removed from it, plus twice H2O. This H2O is nothing but my pure form of water. So let us look at the balancing of this reaction. I have MgHCO3 twice over here. The number of Mg's on my reactant side is 1. The number of Mg's on my product side is also 1. Then I have HCO3 twice. Moving on to hydrogen, I have H2 over here, and I have H2 twice over here. That means 2 plus 2 into 2, 4. 2 plus 4, it is 6. 6 hydrogens on my reactant side. On my product side, I'll have H2 plus H2 into 2. That means 2 plus 2 into 2. 2 plus 4, that is 6. So 6 hydrogens on my product side as well. Then I have carbon, that is C2. Over here I do not have any carbon. That means on my entire reactant side I have 2 carbons. On my entire product side also I have 2 carbons. Moving on with oxygen, I have O3 twice. 3 into 2 is 6. Plus O2 twice. That is 2 into 2 is 4. That means 6 plus 4, that is 10. I have 10 oxygens on my reactant side. Let us move ahead with the product side. I have 3 into 2, 6. Plus O2 is 2. That means 6 plus 2 is 8 plus 2 over here is 10. So 10 oxygens on my reactant side and 10 oxygens on my product side. Even my oxygen is completely balanced. Moving ahead, we have only left calcium on the reactant side. That is 2 calciums over here and 2 calcium over here. That means this is my entirely balanced reaction. Then I have MgCl2 plus CaOH twice forming MgOH twice plus CaCl2. Let us look at the number of Mg's over here. It is 1 and Mg is 1 over here. If I see the reaction, I can see it in a much simpler way by this, that this Mg had Cl2 over here, but now it has OH twice over here. It's a double substitution reaction. That means this OH twice from here has just substituted the place of Cl over here, and this Cl twice over here has just substituted the place of OH twice over here, and this Cl2 over here has substituted the place of OH twice over here. Now we have this reaction MgSO4 plus CaOH twice forming MgOH twice precipitate plus CaSO4. If you have a look at this, this is also a double displacement reaction or a double substitution reaction as we call it. Over here this OH has been displaced by SO4 and this SO4 has been displaced by OH. That means this OH twice will now come with Mg forming MgOH twice, which is a precipitate form, and this SO4 will go and stick itself to Ca forming CaSO4. Again, this is my completely balanced reaction. The last type of reaction is to convert bicarbonate ions of NaHCO3, KHCO3, etc. into carbonates. So over here, let's take an example of a sodium carbonate, that is sodium bicarbonate, which is twice NaHCO3 with CaOH twice forming CaCO3, which is a precipitate, plus 2H2O plus Na2CO3. So this twice H2O is pure form of water, and this CaCO3 can be easily be removed by the filtration of method because this is a precipitate. So over here, let us see the balancing of the reaction. I have twice NaHCO3. So for Na, I have 2 Na on my reactant side. On my entire reactant side, there are just 2 Na, which is over here forming Na2. Moving ahead with H, so I have 2 H's over here and H2 over here. So 2 plus 2 is 4. That we'll get over here. H2 twice is 4. Then we have CO3. So number of carbons over here is twice. And over here, if we see the number of carbon is 1 plus 1 2, again it is twice. Moving on with oxygen, 3 into 2 is 6 plus 2 is 8. Over here for NaHCO3 this is O3, which is twice, 3 into 2 6 plus O into 2, that means 6 plus 2 8. Over here we have O3 plus 2, that means 3 in plus 2, 3 plus 2 is 5 plus O3, that is 8. Correct? 3 plus 2, 5 plus 3, 8. So oxygens on this side and this side are again balanced. Then the last thing we have is calcium. We have one calcium over here and one calcium over here. That means this is my entirely balanced reaction. Reactions with soda. Soda removes all the soluble permanent hardness due to the calcium salts. So over here I have two examples of CaCl2 and CaSO4. Both of these are nothing but my calcium salts. So I have CaCl2 plus Na2CO3 forming CaCO3, which is a precipitate, plus twice of NaCl. Let us see the balancing of this reaction. Over here I have one calcium, over here also I have one calcium, plus Na2CO3. So over here I have twice of sodium. We'll see the number of carbons over here is 1, number of carbons over here is 1, number of oxygen is 3, number of oxygen is 3. This is a very simple reaction and can be easily balanced, but this is my soluble salt CaCl2. It forms an insoluble salt of CaCO3. So this soluble impurity is now converted into an insoluble impurity because of my sodium. Now again I have another reaction of CaSO4. CaSO4 is also a soluble salt in water. This gets converted into CaCO3, which is a precipitate. These precipitates can be easily filtered out later. So now this CaSO4 has a reaction of Na2CO3 forming CaCO3, which is a precipitate, plus Na2SO4. Let us see the balancing of this reaction. Over here I have one calcium on my reactant side, one calcium on the product side. Let us look at the number of sulfur, that is S on my reactant side is 1, S on the product side is also 1. Number of oxygen over here is O4 plus O3, that is 7. 4 plus 3, 7. On my product side I have O3 plus O4, that is 3 plus 4, again 7. And finally the number of sodium over here, Na is twice, Na is twice. Carbon is 1 and carbon is 1. That means this is again a very balanced reaction where a soluble salt CaSO4, it's getting converted into an insoluble salt CaCO3, which can be easily precipitated and later filtered out. Now when we are talking about these lime and soda processes, we are going in detail with it, with its two forms, that is the cold lime soda process and hot lime soda process, which will be discussed in detail in the later sessions. So today over here in this session we studied about a process named lime soda process, which converts the hard water into soft water using two components, that is lime and soda. First we studied about the composition of it, how much of lime or soda is needed, and then we studied the different reactions of lime and soda with the impurities, converting that hard water into soft water. Thank you so much for watching this video. Stay tuned to Ekeeda and subscribe to Ekeeda.